Alrighty guys, where we left off, just stopped at this slide. We were talking about how you can name things. One type of data you can have, and I know we've mentioned this already, is the integer data type. What an integer data type is it's a whole number. And since C has been around since the 70s, back when, it was like invented like in 1969 to 1970, back when you could find a computer where the largest number it could hold might be 32,000, all the way up to now where you can find machines with, 8 gigabytes or 16 gigabytes of RAM in it. The data types have migrated. They have changed. Or I shouldn't say that they've changed, but in the C language, it was never specified what an int was. It's just that an int was a whole number. And then they decided, well, maybe you need a short int as opposed to a long int. And a short int could hold more data, or less data than a long int. And we talked about that, right? The number of bits determines the number of, the size of the variable of the data you can hold. So a short int is 16 bytes long, and it can hold up to it can hold 65,000 different values, from -32 to +32. And normal int nowadays is defined as 4 bytes, which can be from -2 billion to +2 billion. A long int is the same size, which doesn't make any sense. And then a long int is 8 bytes. So that's, it can hold an astronomically huge number, whatever that is. And if you need numbers larger than that, there are data types which support that as well, but they are floating point data types. So at one time, if you used an int, like in the early 70s, it might just be a 1-byte number. That might be 256, a number between 0 and 256, or something like that. And you know how to calculate the number of bits based on the bytes, because there's 8 bits in a byte. So a 4-byte number, 4 times 8 is 32. That's 32 bits. A long is an 8-byte number. 8 times 8 is 64, so that's a 64-bit. So back when your PlayStation first came out and it was the first 64-bit video game system, and it could display one of 9 zillion different colors, then each number was taking up 8 bytes in it. So anyways, we don't have to memorize all this, but you do need to know that there are versions of numbers called unsigned, and an unsigned number can only be positive. If you do not specify unsigned, the number can be negative. If you do specify unsigned, it can only be positive, but you get twice as many to play with. So like if you're looking at an int can go from -2 billion to +2 billion. That's a range of 4 billion. But by saying unsigned, you can play with that 4 billion counting from 0 all the way up to 4 billion. And the reason that works is because the first bit in a signed number, not an unsigned number, is what's known as a signed bit. So say you have an 8-bit number, 1, 2, 3, 4, 5, 6, 7, the 8th bit. If that is a 0, it's considered to be a positive number. If that is a 1, it's considered to be a negative number. So the largest number that a signed data type could have, if it was 8 bits long, would be 1, 2, 4, 8, 16, 32, 64, would be 127. And then if this was set to negative, it would be about up to a negative 127. If it was all ones with a signed bit set, which set this to negative. So you'd have a range of 256 different data bits there. This is not exactly quite true, but it's pretty close to being true. It doesn't only depend upon that. It does something called 2's complement in order to store the bits if it's a negative number. But that's the idea. If the first bit is a 1, it's a negative number. If the first bit is 0, it's a positive number. But that's if it's a signed data type, like int. If it's an unsigned data type, they're saying, well, that first bit is actually data. So now we have yet another bit place to hold. And so it goes all the way up to 128 there. So instead of 127 being the maximum number, 255 is the maximum number. So it can go from 0 to 255. That's the idea behind adding the word unsigned in front of the word int. It gives you twice as many values on the positive end, with the consequence of not being able to have a negative number in there. as far as our programming is concerned, we're probably not going to play with numbers that are larger than 2 billion very often. But I think we did that multiplication problem, you know, where it was 1 times 2 times 3 times 4, and it got too big to be held in an int pretty quickly. So we changed it to a long int or a long int or something like that in order to hold a larger value. Or maybe we just changed it to a float, I don't remember. Anyways, we have all these different data types. Do I really want you to memorize all of them? No, but I want you to know that if an int isn't big enough to hold your data, change it to a long int. And also know that a short doesn't contain as much as an int because it's half the size. So it has a smaller range of data. Is there a reason why you would use a short rather than an int? Is it like, does it save space in the computer? Does it make the program run faster? Not really. You know, maybe back in the 70s when you had, you know, a computer with 64 kilobytes of RAM in it, you might have grudgingly, you know, wanted to use 2 bytes per variable rather than 4 so that you could, you know, put in twice as many variables in. It doesn't matter anymore. So variables of the same type. If you have more than one variable of the same type, like say you have a variable called min, a variable called max, and a variable called counter. You could define all 3 of those on lines by themselves, like this, in which case you would do that. Int min, int max, and int counter. Or you could declare them all in the same line if you want. Int min, comma, max, comma, counter. Both ways are equally valid. Is there a reason to choose one over the other? Well, the only reason I can think of to do it this way would be if you want to put comments. Like, this is the minimum temperature. Whatever, you know. This is the maximum temperature. This counts things. Okay, that's stupid, but you know what I'm saying. If you had lot of different variables of the same data type, but you wanted to put comments about what they were, then lining them up like this wouldn't be a good idea. Otherwise, there's no advantage to doing it one way or the other. And you'll see me do it sometimes this way, and you'll see me do it sometimes this way. Since I'm trying to get the most on the screen as possible, so that I don't have to scroll up and down with y'all watching it, I may do this more often than I would, you know, in the real world. But if they're of different types, they have to be in different definitions. So if I had an int and then I had an unsigned int, you know, this is my int, and I'm going to call it IA for integer A. And then I had an unsigned int int A. They have to be on separate definitions. There's no way that I could do that just separating them with commas. You know, and if I had another data type completely, like a string, that'd also have to be a separate definition. The only time you can do something like this is when they're all 3 the same. Now you can initialize your values as you declare them. You can say, okay, my minimum is 0, my maximum is 100, and my counter is going to start off at 1. Well, you could do the same thing if you declare them in one line. My minimum is 0, my maximum is 100, and my counter is equal to 1. Either way, there's nothing to argue for one over the other unless you're going to be using comments, which means that you lend yourself to doing that. So here's a program. It's got a variable called checking. It's got a variable called miles and a variable called days. Our checking account has negative $20 in it. We've traveled 4,200 miles, and it's been 189,000 days since Columbus stood on the spot. That's all silly, but I guess we're saying that there's no such thing as a negative distance, so that's why we made it unsigned. But your checking account can have a negative value, so that was not made unsigned. I generally forget to put unsigned. You know, I don't really care if my numbers get negative or not. And then days does not have to be held in a long because, well, for one thing, if we remember back here, there's no difference between an int and a long in the current version of C++ that we're using. A long is 4 bytes, and so is an int is 4 bytes, so they both can count up to 2 billion. So there was no reason for the programmer here to make that a long. And if Columbus had stood here 2 billion days ago, you know, more than 2 billion days ago, that would be really interesting. Don't know why. Can't explain that one. So this is just an example of creating 3 different variables, defining 3 different variables. Nothing more interesting than that. Integer literals. If you type a number into your program and you don't put a decimal point in it, and what I mean when you type it in, if it's in the source code, it is a literal and it is an integer literal. It's an integer literal because there's no decimal point on it. So when we see checking equals -20, -20 is a literal and it's an integer. Miles is equal to 4276, 4276 is an integer. Even if we're copying it into a floating point, that number right there is literal. Excuse me, that number right there is in an integer. That's what's important about it. Okay. Integer literals are stored in memory as ints by default, not longs. If you need to put it into a long, you suffix it with an L. If you need to put it into a long, you suffix it with 2 L's. If you want to pretend, or not pretend, if you want to dictate that it's a hexadecimal number rather than a binary, rather than a base 10 number, you precede it with OX. So say that I have a variable called X and I want to set it equal to 255. And I have another variable called Y and I want to set it to the same value, but I want to do it in hexadecimal. Well, OXFF in hexadecimal happens to be 255 in base 10. So just preceding it with OX means, oh, by the way, I'm giving you a hexadecimal number. And if you have a long int and you want to store a really huge number in there, then you would suffix the number that you were storing in there with 2 L's. Are we going to do much of that? No, not really, because I can't think of very many uses for a long. That's such a silly data type, long. If you use a more modern language like Java or C#, then the data types have been cleaned up and you don't have 20 different integer data types. You just have a couple. The char data type looks like char, but we say char for character. That holds exactly 1 byte. And 1 byte is large enough to hold 1 ASCII character. 1 character that we type in from the keyboard. That's why it's called a char. It holds 1 character. You put single quotes around it rather than double quotes. So the char data type will hold exactly 1 character. Something like, an A, a Z, a 1, a hashtag, whatever. All of those are 1 character. We don't actually use the character data type as much as we do strings. And the reason for that is a string is a series of more than 1 character. Usually you're letting people type in more than 1 character. This is stored in memory as the ASCII value of that letter. And I haven't given you a long lecture about ASCII yet. We will probably hit that at a certain point, or not a long lecture about it. But when data is stored on a computer hard drive or in memory, it's just a series of numbers. And you have to decide, okay, if I'm going to write out an A, what number am I going to choose for A? And if I'm going to write out a B, then what number am I going to choose for B? And so on. So during the 60s, the programmers decided upon making a common table that everybody should follow, so that if you were going to write out an A, it would be a 65, and a B would be a 66, and a C would be a 67, and so on. So if you're going to write the word dad out in memory, there'd be a 68, followed by a 65, followed by a number 68. Or the hex versions of the same values. The D is a 44, the A is a 41, and the D is another 44. So when you talk about a text file, this is a text file here. I'm going to save this, and I'm going to upload it to what's known as a hex editor. So these are the June 15 notes. This is saved in text format, meaning it's saved in ASCII format. So the very first character in the file is an I. An I in ASCII, if we look it up, well, it's a lowercase I. So it'll be a 69. Because when we load it up in a hex editor, we'll see the hex values of these. There are other data formats, of course. If you save the same data as a Word document, it's a completely different, I don't know, yeah, here we go. It's a completely different data format. The format of the file is completely different. It's still ultimately just a series of numbers. But here's my file saved as a Word document. Do file, save as, save it in the C++ directory. I'm going to call this, I'm just going to call it junk to remind myself to delete it. Alright, so if I go to the command prompt, type CMD into the start box, and I CD into that directory where those files are stored. If I look for my text file, there it is, June15 notes.txt. If I do this, type June15 notes.txt, it echoes the contents of that file to the screen. It's a text file, so it can do that nice and cleanly. But if I tried to do the same thing to that Word file, there are some Word files in here, but I specifically wanted the one called junk. There it is. So if I type junk.docx, it looks like garbage. All of that means something, but it's not ASCII text. So you can't pop that open with an ASCII text editor. Our program editor inside Visual Studio, or if you're using a Mac or Linux or whatever your program editor, will edit ASCII files. You're creating text files. The source code for C++ is just assumed to be a simple ASCII text file. So we have this file here. It's a text file. It's got all this text in it. I'm going to load it up in a hex editor. There's one that's real easy to find. hexed.it. Okay, I'm surprised some of y'all aren't watching this. I don't know. Maybe it's fascinating to me and not y'all. Okay, so I went to this site. I do open file. And I go into the directory with my file. Here we go. June15 notes. Over here we can see all the text that was in that file. It started with an I, like I said. I'm going to pull that back up. Here it is. Int min is equal to 0. Int max is equal to 100. We see that there. Int min equals 0. Int max is equal to something else. But here's the hexadecimal versions of it. An I is a hexadecimal 69. An N is a hexadecimal 6E. A T is a hexadecimal 74. So if we go back here, this is saying that if we declare a variable called letter and we store capital C in it, it's got a 67 in it. Well, if we go back to here and look at our ASCII chart, we'll see that a 67 is, in fact, a C. So the data is stored for the basic char data type as an 8-bit ASCII character. Now nowadays there's more than one type of text data. People write in Japanese and 20 different flavors of Chinese and German and stuff like that. And this ASCII table only has pure English characters. It doesn't even have the German umlauts and the Italian diacriticals and the Spanish N with a wavy bar over it. So there's far more characters in all of the Earth's languages than could just be fit in 255 different characters. So they came out with something called multiple byte character sets. In a multiple byte character set, you can use more than one character to specify a letter. So if you're writing somebody a love note in Klingon, then actually I don't think Klingon is part of Unicode, the multi-byte character set, but it ought to be. If you're writing somebody a love letter in Russian, they're not going to look the same as ASCII text. They can't only be held in one byte. So the C++ and especially Microsoft Visual Studio has come up with different character types for holding multi-byte character sets. But we're going to ignore all that for now, and we're just going to assume that a character is a single byte that holds a single letter. If you type in a single quote, the Visual C assumes that what follows is going to be a single character followed by another single quote. Anything else than that could be considered a syntax error and might not compile. Here's an example. They define a variable called letter. They store an A in it. And then to see out, they copy the A and then they copy a new line. So it would print an A on the screen. And then they change that variable to hold a B and they do the same thing. They write the B out to the screen. A character string is a series of characters ended by a 0. It's called a null. It's called the null terminator. Otherwise, how would you know when this stopped if you were a computer? You know, how would I know that there were 5 letters in this string and then the next one might have 4 and the next one might have 8? There has to be some way of telling the computer that the data stops. And the way that the creators of the C language decided to do so was that you would have a series of characters followed by a 0, a null character. And so a string is held within double quotes rather than single quotes. So single quotes are for characters, double quotes are for character strings. The C++ string class. I really hate going through PowerPoints. I actually like, writing the program and having y'all look at the program. Anyways, okay, but I guess we got to do both. The special data type string supports working with strings, and this was not included in early versions of the C language. But now there's a data type called string, and you can declare your variables as strings, and you can hold series of letters in them, and they can be displayed just as easily as any number, like that. And so what do you store in a string? Well, somebody's name, somebody's address, stuff like that. Alright, as soon as we get past this one, I think we're going to try to do something in class together. Floating point data type. Well, an integer is a data type that doesn't have a decimal point, so it cannot contain a fractional number. A floating point data type does have a decimal point. So it can have fractional components, like 12.45, minus 3.8. This is calling this real numbers. Inside the computer, it's stored in a form similar to scientific notation. So if you've taken a math class recently or done chemistry or physics where you had to do 3.1 times 2 to the 10 or whatever, inside they're stored like that. And that means that there can be some rounding errors that happen when numbers are added. It's not a big deal, but we may run across an example of that. There are 3 types that we are concerned about that are floating point data types. There are float, and then there's double, which is a bigger version of float, and then there's long double, which holds larger numbers still. A float is a 4-byte data type. It can hold any number up to 3.4 followed by 38 zeros. So 3 followed by 38 zeros, quintillion, zillion, billion, whatever that is. That's far larger than the maximum of an int or a long int or whatever. And then the double is got twice as many bytes in it. So instead of being 4-byte data type, it's got 8 bytes, which could hold a really large number. It could hold a 1 followed by 308 zeros. Now, I don't want to have to type a number that's got 308 zeros. But if you're dealing with astronomically huge numbers, you would want to make it a double. So when we were doing our program that kept multiplying numbers by each other, getting larger and larger and larger, I think I had us change the data type to double. I'm not sure if that's how I got around the fact that it was ending so early. But you can see why it would hold so much larger data. The maximum value of a long int, if we scroll way back up here, is, okay, how many zeros is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So a long int can hold a 1 followed by 19 zeros, whereas a double can hold a 1 followed by 308 zeros. Huge number. So double is the largest data type which we will be dealing with. There are libraries for using larger numbers still, but we won't ever need any of those in this class, probably in your normal programming career. If you want to type in a floating point number into your program as a literal, if you want to hard code it in the text of your program, you just put a period there. Or you can use an exponent if you have to. If you want to force it to be a double, you can put an L there. I'm not sure why they didn't make D. Okay. And then there's one last data type called bool. A bool is either just true or false. Used to be that programmers would use 0 and 1, and they would treat zeros as false and ones as true. But so many programmers would redefine the word false to mean 0 and the other word true to mean 1 that it eventually just got built into the language. And what do I mean by define? Well, I saw one student doing this, and I need to show the rest of y'all that you can define, well, here, using preprocessor directives. Spacing out, where's Visual Studio? I guess I never, oh, I see it, I see it. There we go. Third one down. Might as well get the boilerplate code out while I'm thinking about it. I'm going to make a new project. It's an empty project. I'm not even changing the name of it. It's just going to be called Project 1. But I did choose C++. Then I'm going to create a new file. So I'm going to right click on the Files folder and choose New Item. Add New Item. Choose C++. Paste in our boilerplate. And there we go. Now our program from Wednesday looked something like this. We had a min, we had a max, and we had a counter of some kind, which we set equal to min. What if these values were going to be shared by more than one program? What if you had 20 different programs that all depended upon the minimum being 1 and the maximum being 100? Well, you would want to stick those things in a header file. And one way to define them in a header file would be to use preprocessor directives known as #def, #define. And you could say my minimum is a 1, and #define, my maximum is 100. Now, pretty much by agreement, all programmers make their #defined values capital letters. So that's why you saw me type min there and max there in capital letters. And then if I was going to write my loop, while counter was less than or equal to max, then I would have it do something, you know. I might have a sum, or I might at least write it out. You know, I'm going to write the number out to the screen. Write the counter out, followed by ENDL. Now this program would count from 1 to 100. So this is what #define does. It's a preprocessor directive so that when the program compiles, everywhere it sees the letters MIN, it replaces it with a 1. And everywhere it sees the letters MAX, it replaces it with a 100. And you could do some kind of weird things with that. You could make it so that your program was incredibly difficult to read. Say you decide to define a data type called glarg, and you said, okay, everywhere the word glarg appears, okay, don't do this because this is just really asinine. There you go. You know, now we're making it look absurd. And then we could use #define, you know, blah to mean those things. And so everywhere we wanted a pair of parentheses, We could put blah. There we go. And the program would still compile and run. It almost looks like we're writing our own language. We're not really. But what we are doing is we're creating places to where things that we have defined previously will replace those occurrences. So everywhere it saw this word glard. When it was compiled, during the pre-processing step, that's why it's called a preprocessor directive, all of the occurrences of glard would be replaced with int. And then also as it's compiling, all occurrences of the word blah would be replaced with parentheses. And so you could make the language look absolutely goofy if you set up here and you created a whole bunch of pound defines that made it look different. Is there a reason for doing that? Not usually. But people used to do this. People used to do pound sign define, true, 1, pound sign define, false, 0. And that way they could create a variable, you know, like, I don't know, is character alive. You know, alive is equal to true, like that. And then later on there could be an if statement, if alive is equal to true. That was before the invention of the bool data type. Now you just do the same thing with the bool data type. So you don't do it like that. You do bool alive is equal to true, lowercase. And you do, you know, if alive is equal to true, this would be in lowercase as well, like that. There's just about no reason to redefine true and false like that. So those are preprocessor directives. Pound define means I'm creating a variable, excuse me, I'm creating a string of letters that I want replaced by the symbol that follows it when the program is compiled. And there's another one called if-def, so that if something is already defined, you can do something else. But we'll get to that one later. There's no reason to talk about that one for right now. Go to the Dropbox, and in the in-class assignments, look for F. Refresh your Dropbox if you have to. There's a document in there called in-class assignment F. Now it's a tutorial for creating a Visual Studio application, so it shows all the menus and stuff like that we have to do. But we already know how to do all that. So what we're going to do this one's really trivial, isn't it? Okay. Is we need to get this part of the program, the stuff in step 11, into our Visual Studio project. So I'm going to make a new Visual Studio project. Well, I've already got one here. But I'll make a new one. New project. I'll call it in-class F. It is an empty project. In source files, add a new source file. I don't care about the name of the source file, except I'm going to add my initials to it. JGT, source.cpp. Now go and grab the code that is on step 11. And paste it in to your source code file. Now this is a really dumb little program. It calculates how many pounds you have gained per year over your entire life. So if you're 20 years old and you weigh 200 pounds, you've gained 10 pounds per year. That's dumb, but it just shows using cout and cin. And it shows different data types. It shows using a floating point data type and an integer data type, and it's got a string. So I've got all of that in there. There's no system pause there. So I'm going to go ahead and uncomment out the line. It's 3 lines up from the bottom so that system pause will be there. So if I did everything right when I run it, eventually it'll compile, hopefully. and here's the way the program works. Please enter your name. My name is Joe. No, it's not, it's Jeff. Please enter your age, whole numbers only. Well, I'm older than I want to admit. Please enter my weight. I weigh 400 pounds. There, Jeff, you've gained about 9 pounds per year. So that's a real silly application. But your homework is going to be a little bit more serious. What your homework will do is it calculates something known as your basal metabolic rate, which is how many calories your body uses per day on average. And that depends on your weight and also your activity level. So, you know, if you have an athletic build and with a lot of muscle, then you burn more calories a day, even at rest, than, you know, somebody who is very sedentary and doesn't do much. So we will look at that programming assignment in a little bit. So let's look at this. It looks pretty standard. We have IO string, we have using namespace STD. There's only one extra thing that we tacked onto it, which is so that we could use the string data type. We did # include string. So we probably ought to add that to our boilerplate if it's not already in there. I forget. It's not, but I'm going to put it in there so that the next time I copy and paste, it is in there. So # include string. We will be using strings from now on, so I'd like to have that in there.
Where should I save that to so that I just stay on my computer every time?
Well, it'll be on your computer every time. So I would just save it to the desktop or something.
A lot of my stuff has been disappearing over the days.
I think they're in deep freeze.
Oh, great. Really?
I have a thumb drive.
I apologize, guys. I didn't know that they had reconfigured the computers to do that. That is a real drag. Let's see, what can we do about that, if anything?
Like a Dropbox folder for it or something? If you download it?
Yeah, you can upload things in. There used to be something called a file vault as part of D2L where you could put your files on. I'm not seeing that right now.
The locker, yeah.
The locker, yeah. Okay, under course tools, click on course tools and then locker, and you can upload files into the locker. So you could stick your boilerplate code there and it'll be available on any computer that, you know, you can access D2L from. Wow, some of these date back to 2012. I wonder what I was doing 4 years ago.
You sure you want to know?
Not really. I'll probably delete all those. Anyways, okay. So that's a good idea. I need to upload my boilerplate there so that I can access it each time. You really ought to make the boilerplate available for everybody. I'm going to stick our boilerplate inside our contents under Unit 1. So if you need to find it in a hurry, just go to our class and under content quick links, click on Unit 1 and you'll see boilerplate and you can go and copy it out of there. So the program has its # includes, and we know what those do. Those bring in other files to give us extra capability. Specifically, what does IOStream bring us? Well, among other things that we don't see, it brings us the ability to use cout and CIN, and also that ENDL thing that we use occasionally. And what does # include do? It brings in the string data type. And what is using namespace STD? That just means that we don't have to type STD in front of cout and CIN. If that was not there, then the code would no longer compile until I went over here and I typed STD : in front of that, and STD : in front of that, and STD : and so on. And if you Google up code on the internet and you're looking for help, you'll see people do that. And you may wonder why they just didn't have that. Well, some people don't like putting using namespace STD in there because they want to control exactly what gets brought in. And if they have their own string data class, they don't want it assuming that when you type string, it's using the one out of these libraries. They want to be able to define their own. So a lot of times you'll see code on the internet that does not have using namespace in there, and that's why you'll see std : in front of a bunch of stuff. But for us, it's easier to type if we leave that there. And so then there's our main function. Every program we write will have our main function. Main has the ability to have things extra, command line parameters passed to it. And if you needed to make your program sensitive to command line parameters, you would need to add something specific between those parentheses to pick out those parameters. What is a command line parameter? A command line parameter is when you're running a program from the command prompt, like dir, that's actually a program. You can add on extra things to make it behave differently. Like if I want these sorted by name, I could do dir/order by name /on. And now my directory is sorted by name. Or dir/order by date /od. Well, when you run your program, you could be doing it from the command line, and you could be passing in those optional parameters to make it do different things. And so you would need to do that to know what to place between the parentheses there in order to get that to happen. Then we declare our three variables. We have a double, which is a floating point, and we have an int, which is an integer data type. Why do we have this as a floating point type? Well, people might really care, I guess, that they weigh 155.3 pounds. They're really picky? I don't know. But age, people don't usually go, well, how old are you, dude? I'm 22.4 years old. They usually just say I'm 22 up until it rolls over and they hit 23. So that was defined as an int. And then since we asked them their name, that was stored in a string. And we've seen how to do this part. In order to prompt for the name, we have to display a message and then allow them to type in something. These two things right here put together consist of prompt. That's displaying the output, sending it to the quote output stream, and this is reading from the input stream, console out. Cout stands for console out. Cin allows it to read it back into the name. So please enter the first thing it does. Tell you what, if you have this program up and running, click here on the gray bar next to the number 17. That puts a red dot there. That's known as a breakpoint. Or you can right click in that gray spot, right? That's not letting me. Okay. You can delete the breakpoint. What is a breakpoint? Well, when you run it in debugging mode, when you click this green arrow up here and run it in debugging mode, it will stop at that point. So now I'm going to run it by clicking the green arrow. The program is going to run and it's going to stop at that specific point. And it hasn't done anything yet. Down here we find the output window. It hasn't displayed anything yet. That's because it stopped at this line before executing it. Now I want it to execute that line. Well, I need to find the option up here in the menus that will skip to the next line. See if you have these little buttons up here. See if you have the little arrow followed by the green circle with a dot and the other circle with the dot and the hook with the dot. If you have those, great. Do y'all have those on yours?
They're grayed out.
Pardon me?
They're grayed out.
Oh, the grayed out. What happened when did you?
I'm not running the program.
Okay, yeah. Go ahead and close this,
User error.
and then choose Windows Debugger. It's not stopping there. I don't think that's user error. I think that's confusing.
I stopped the program again and it came back up.
Oh, I see.
My line
You didn't.
17 is not the
Your
same
line
as yours.
17 is different than mine. Okay, okay. Yeah, don't go by my line number. I don't know what I have at the top of this program. Maybe I put some blank lines or something. Oh, I put this block. Okay. Anyways, where I want you to put the red dot is on the place that says please enter your name. So yours worked when you did
Yeah,
that.
there we
Okay.
go.
Okay.
Yeah.
So you have these options here that if you hover your mouse over the little symbols, you can read what they are. One of them is step over. That just means go to the next line. And you can see that it's also supposed to be F10. However, F10 on some of these machines are programmed to do something different, which is a drag. I'm going to hit F10 and see if it works, because it's easier than clicking that big button each time.